Welcome to the course. I'm very happy to see you all here today. Especially happy since it's party time in UCLouvain. So you guys are the serious ones. Today I want to talk about causality, causal reliable broadcast, adding one small adjective to reliable broadcast. But before that I want to refresh some things from before. First, a few seconds of respect for the Ukrainians who are fighting for their freedom, still fighting for their freedom. Okay. So one thing, this is kind of for the rest of the course. Remember I talked, we sometimes need a perfect failure detector, we sometimes need an eventually perfect failure detector. It's okay. Sometimes we don't use failure detectors, we'll see that. So we have names for that, where we combine the crash, the failure model, and the failure detector we have. We call fail stop. Fail stop is kind of the best when we have crash stop and a perfect failure detector. We call fail silent when we have crash stop but no failure detector at all. Okay, we'll see that. Sometimes that's very nice. We can get away with it. And then fail noisy, it's crash stop with an eventually perfect failure detector. Why is it noisy? Because this guy, eventually perfect failure detector, can make mistakes. So the mistakes is like noise. It's fog, it's making things kind of messy. So this is called fail noisy. And then we have a final one for disks, where we use crash recovery. Remember this one, where we have a stable storage, and this one we have stubbornness. So this one is used for disk, okay? And like I said last time, so this is synchronous, asynchronous, partially synchronous, that a principle for the course is that we're going to go from P to eventually P. Okay, so we're going to assume fail stop, a perfect crashes with perfect failure detector, and we give algorithms for that. Okay, so we'll always start like that. And that will give you very nice, simple algorithms, and then we'll try to push it and make it use an eventually perfect failure detector. Okay, sometimes it's possible, sometimes it's not possible, but sometimes we need a new idea, but we will change something to use an eventually perfect. So this is very nice because the first one, the perfect failure detector, is simple, okay? And the algorithms are very, very straightforward and nice and clean. But then when we use eventually perfect, things get a lot messier. And so it's interesting to do it like that in two steps, okay? Okay, let me finish what Mathieu started last time, okay? So Mathieu presented reliable broadcasts, but I have the impression he didn't really talk about the uniform reliable. So uniform, okay, well let me define. So the reliable and it works, let me go to uniform. Uniform is a very interesting principle. For many algorithms, we have a regular version and a uniform version. And the uniform version, it is a stronger algorithm. And the uniform version says if the failed node does it, whatever the algorithm wants to do it, then every correct node will do it. So a uniform reliable broadcast says if a failed node delivers, then all the correct node delivers. Whereas the regular reliable broadcast does not say this. It's only, we know that all the correct nodes will deliver or not. So we don't talk about the failed nodes in a regular reliable. So the uniform is actually harder because the node might deliver the message and it might fail right just after that. So how do we know it delivered it, okay? Okay, so URB delivery is, okay, all the correct nodes get the message. Okay, so if a failed node gets it, then every correct node will deliver it. Okay, so we have to know at least that all the correct nodes got the message. Okay, that means we have to find out when the correct nodes get it. Okay, that means we need acknowledgements. That means we can't just deliver, we have to send acknowledgement first. Okay, and we have to collect the acknowledgements, and when we know that all the correct nodes have got it, then we can deliver. And then we know that we've satisfied the condition. Okay, because if the node fails afterwards, it will still deliver, and we have to satisfy the uniform condition. Okay? And to do this, we use a perfect failure detector in the first algorithm, and we have a function, can deliver. This function is if the correct nodes is a subset of the acknowledgements. So the way to read this is, if all the correct nodes have acknowledged this message M, so we're going to get acknowledgements from the message, and we also keep track of correct nodes from the perfect failure detector. So if all the correct nodes have acknowledged, then we can deliver. And then we satisfy the uniform condition. Okay? So the code here, so here at the top, here, I can use this. Okay? So here I do uniform reliable broadcast, and this triggers a best effort broadcast. Okay? And I have a pending message here, a pending set. Okay, and when I have a best effort deliver, what I do is, this is actually an acknowledgement, okay? And then I actually can do a best effort broadcast. So basically I'm making sure that everybody knows that I've got it, okay? And then there's a final condition. If I have a pending message and I can deliver it, that means I get all the acknowledgements, then I do. And then I, of course, have the condition here that we don't have duplicates. So there's this very nice can deliver condition, okay? But this one needs a perfect failure detector, okay? So here, deliver when all the correct nodes have acknowledged. So can deliver means all the correct nodes have acknowledged, okay? But that depends on the perfect failure detector, okay? So we can show the correctness. So again, we look at all the conditions in the specification, the no creation, no duplication, that's easy with the delivered set, okay? And then if a correct node best effort delivers, then it eventually URB delivers, okay? There's essentially a chain, okay? So the correct node, best effort broadcasts, okay? It gets the BEB delivered for every correct node, and then because we're using a perfect failure detector, it will not wait forever for the dead nodes, and so it can know when it gets the acknowledgements, okay? Okay, so the other two conditions, validity and uniform agreement, basically you have to go from the URB layer to the best effort layer and look at the condition. So let me show you an example here, the eager algorithm. So I have a URB broadcast here, so I send here, this is doing best effort, here and here, and these two also do best effort. So these are sending acknowledgements. So you have an acknowledgement coming back here, and an acknowledgement coming back here. So here you have the two acknowledgements, and these two nodes are correct. So you have URB deliver. Here you have the best effort here. You have also the acknowledgement here. So the 1, 2, and the third one. So there's a URB broadcast. So this is getting 1, 2, getting both the correct nodes. So this can URB deliver, and this one also gets 2 messages from P2 and P1, so it can URB deliver. So the 3 have satisfied the can deliver constraint. Okay, so now this is a perfect failure detector model version. So what about eventually perfect? Okay, actually we can do even better than eventually perfect. We don't need a failure detector at all. And we're going to use a new concept for that. I'm going to show you an algorithm for fail silent. That means we have no failure detector. The node just stops working and we can still do URB. But we have a new concept that we use. This is the concept of a majority, okay? And it's nice to introduce it here because this one will be very important later when we talk about consensus. So the notion of having a majority of correct nodes. So there's no failure detector. We don't know if a node fails, but what we do know is that the majority of the nodes are correct. So the majority means strict majority. Yeah? So if we have 11 nodes, then we know we have 6 correct nodes. If you have 12, there's 7 correct nodes. So we have a strict majority of correct nodes. Okay? And that is going to be enough. So I'll show you how to do it. Okay, so the algorithm is quite simple. When a node receives acknowledgement from a majority, it can deliver. That seems very simple. So how come it works? Okay. Well, the algorithm is exactly the same as before, except we're only going to change this can deliver function. Okay. So I introduced this can deliver here in the previous algorithm. When all correct nodes have acknowledged, then I deliver. Okay. That gives me the uniform condition. But now we change that. It's when a majority have acknowledged. Okay. Majority is acknowledged, then we deliver. Okay. So how do we know that the uniform condition is satisfied when we got in a majority? Okay. Okay. The trick is the following. Two majorities will always have a non-empty intersection. There's always one node if we intersect the two majorities, because we have two majorities here. Huh? If I get acknowledgement from a majority, but I also know that there's a majority of correct nodes. You see, I don't know which ones, I know it's a majority. So I got acknowledgement from a majority, but I know that there's a majority of correct nodes. And there must be one node in that intersection. That means from the majority I got, I know at least one must be correct. Okay, because there's a majority of correct nodes. And that one, which I call P, will itself ensure that all correct nodes get the message. So the best effort broadcast will work from that correct node. Remember, a best effort, when the sender is correct, then it's able to send to all the correct nodes. Okay? So you see this very interesting technique where we have intersection of two majorities. Huh? You see there's two majorities here. Huh? This is a really important technique. And this technique is going to come back over and over again. And this is something that's going to help us a lot when we do internet algorithms. Okay? So you got acknowledgement for majority, but since the majority is correct, that means at least one node in that majority that you got must be correct. Intersection of two majorities is at least one node. Okay? Okay, and that's it. So I wanted to say that. So I don't think Mathieu was not able to talk about that, but it's important. It's an important concept. Okay? Okay, so uniform, reliable broadcast, you can implement it with no failure detector, just on top of best effort, assuming a majority is correct. That's pretty good, huh? That's pretty robust, huh? If I have 12 nodes, then 5 are allowed to fail. That's fairly good, okay? 7 have to be correct. And so this technique is a very useful, important technique, okay? Okay, now I want to talk about causality. I want to add something to reliable broadcast. I want to make it causal. And it's going to be fairly straightforward to do that because I'm going to build on top of reliable broadcast. Remember, I have layered structure. So the event component model that we used has layers, and the idea is that each layer adds a small thing to the previous layer. So we're going to use reliable broadcast, we already did it, and we're going to add causality with a small layer, okay? So what does it mean? So here's an example, a chat application with a group of people who were discussing something. So I received this. Ali says, "Are you sure?" Not E. That's weird. Mrs. Y says, "Auditorium D." And Mr. X says, "Does anyone know where the lecture is today?" So these messages are mixed up. In fact, Mr. X was the first one to send the message. He says, "Does anyone know where the lecture is?" And Mrs. Y answered to that saying, "Auditorium D at Forum." These are real places, huh? This course was also given at KTH in Sweden, so these are real places. I can replace this by Barb, and this one by Mercator, if you want to. And then the final one is Ali replying to Mrs. Y, saying, "Are you sure it's Auditorium D, not E?" Because he heard it was E, okay? So there's causality here. So between these three broadcasts, there's a causal connection. So remember, we defined causality, yeah? And we said in a distributed system, causality is really the most important thing, okay? Okay, so we want an algorithm that respects causality, a broadcast algorithm that does not do this, okay? Okay, but we have already some broadcast algorithms, right? We have a kind of sophisticated one called uniform reliable broadcast. So does uniform reliable broadcast solve this problem? Will uniform reliable broadcast respect causality, so not do this? Will it? Can you reason about that? Can you tell me? What do you think? So, will it or won't it? And why not? Or why? Uniform reliable. Remember, uniform reliable, when I broadcast, it's all or none. And if any failed node delivers, then all correct nodes have to deliver. Okay? Fine, that's uniform reliable. Does that respect causality? What do you think? I can give you a small hint. So the uniform reliable property is about single broadcasts. I do a broadcast and I have an all or none condition on that broadcast. But causality is connecting multiple broadcasts, okay? So I do a broadcast and then there's another one after. So what do you think? Does uniform reliable say anything about that?
But the first one can fail and the second one can work. And then you lost the causality between the first one and the second.
But the first one will satisfy uniform. So basically, yeah. So you're saying that the first one might be nobody is getting it. So then it's like it was not sent. Okay? So I'm not respecting causality then. But what if what if the first one does get through? What about what about the second one then? Assume the first one does get through, it is received by all correct nodes, and
all correct nodes needs to broadcast, so it will work.
Will there be a causal connection? No, remember that when I send a message, I don't know how long it will take, okay? So if I do a uniform broadcast from P1, maybe it's very slow. But if I do a uniform broadcast from P2, maybe it's very fast. Okay? So let's say P1 sends a message to P2, P2 gets it, and then P2 replies to that message. okay? But P2 is very fast, but P1 is slow. That means P1 will get the acknowledgements, but very slowly. For some reason, it's very slow. But P1 will be very fast. That means some nodes will receive P2 before P1. There's no guarantee. P2 will not wait until P1 has arrived. Huh? Each node waits only to get acknowledgements from correct nodes. It doesn't, the P1 broadcast doesn't care about P2 broadcast. Okay? So basically, it means that uniform reliable broadcast does not guarantee anything about causality. In fact, we don't know how long the messages are going to take. So if you do a later uniform reliable broadcast, it might arrive before the earlier one because it's faster. Okay. So there's no guarantee. Causality, we know if there's two messages that are causally connected, and one is applied to the other, then we have to force that order everywhere. We have to guarantee that the second one will arrive after the first one, even if the messages are, if the second one is very slow and the second one is very fast, the first one is very slow, then the second one has to wait. Okay, we have to force that. So uniform reliable broadcast does not solve this, because it's only looking at single broadcast, and single broadcast, we don't know how long it takes. And the two broadcasts done one after the other can be very different in terms of time. So the causality, we have to force the message deliveries to be in the same order as they were sent, okay? Even if one of them is very slow, the fast one should wait then, okay? So we have to add something new. So uniform does not make it causal, okay? So causality, it's the same as the relation we saw before, okay, basically. Remember the causal relation? We defined it for all events in a distributed execution, huh? Two events on the same node, a send and a receive event, and then transitivity. Remember that? Now we're going to do variation of this, because now we're interested in the broadcasts. Okay. So M1 is a broadcast message, M2 is another broadcast message. If they're both broadcast on the same node, then M1 is causally before M2. So we're interested in the order of M1 and M2. Okay? But broadcasting M1, it can cause a lot of things to happen. There's an algorithm running underneath with lots of events. And those events are also causal and so on. But we're not interested in that. Remember the definition we did for causality was for all events in a distributed execution. The one we did before, if you look at the whole execution. But here we're not interested in all those events. We're only interested in some of them. We're only interested in the broadcast, the messages that are broadcast, okay? So we did make a kind of a variation of our definition of causality, and it's only looking at broadcast events, okay? But otherwise it's a very similar definition. So if some process broadcasts M1 before broadcasting M2, that's on the same process, then clearly there's a causal connection. Huh? I send a message and then I send a later message. Well, the second one is later. Then there's the network order, okay? If I receive a message, so the process PI delivers M1, which comes from somewhere else, huh? And then, so I see it, so I get the message from Mr. X, and I'm Mrs. Y, and I make a reply, which is another broadcast. So that is also a connection. Someone receiving the message, we say the process delivers the message because it's not the node receiving it, it's the application on the node that gets the message. Huh? It's delivered, and that application does another broadcast. Well, there's clearly causal connection there. And the final one, there's a transitivity rule. If I send a message and then someone else receives it and replies to that, and then a third person receives and replies to that. I have 3 messages, and clearly the middle one is in between the other 2. So we have a transitivity rule also. This is what makes causality hard. That everything is connected, in fact. Transitivity makes lots and lots of connections. Okay. So the causality, so you see the difference and the commonality between the definition we made before. Before it was for all events of the execution. Now we're only looking at the broadcast events. Okay? So we have an interface, causal order broadcast, causal order deliver. So here's the causality property. If a node Pi delivers M1, then Pi must have delivered every message causally preceding M1 before M1. That's clear. So if you look at all the messages that are causally before M1, according to this definition, they must have been delivered before M1 is delivered. So that is the causality property of the broadcast. Okay? Okay, so this property by itself is not enough, So what is this property? What's the easiest way to satisfy this property? Now I'm back to safety and liveness, So this property is what? Well, one trick is to notice it's an if-then. If something, then something. What's the easiest way to make an if-then true? Is to make sure that the if part never is satisfied. Then it's vacuously true. If no node ever delivers M1, then this property is true. So what kind of property is this? Oh, come on. Now you're disappointing me.
Implication.
There's 2 possibilities, safety or liveness. So you can only have 50% chance of a mistake, okay? So what is it?
Safety?
Yeah? Safety. Okay, and why is it safety?
Because if you never deliver...
If you never deliver, then it's satisfied. But you don't get anywhere either if you do that. So the easiest way to satisfy it is to do nothing. Okay? So that's clearly a safety property. So this property is not enough by itself. Okay? What it means is we have to add it on top of the broadcast properties. Okay? Okay, so this is safety. Okay, so what we're going to do is add CB on top of the broadcast. So it's like an extra thing that we add to the reliable broadcast properties. Okay, but let me make sure that you understand. Let me go back to this definition here. So there's FIFO, there's network order, and there's transitivity. So let's do some exercises. So here I have 3 nodes. P1 is broadcasting M1, and then M2. So clearly, the M1 is causally before M2. Okay, and I have 2 possible executions. Okay, now one of them is respecting causality, and the other one is not. So which one is not respecting it, and which one is respecting it? So this is an exercise. You tell me. So FIFO order means that it's delivered in the same order that it's broadcast. Yeah?
The one that respects it on the right.
Yeah, the one that respects us is on the right. Okay, because M1 is delivered before M2. And here, it's funny, but M2 will be delivered before M1. So this one on the left does not. Yeah, that is correct. Very good. So the one on the left does not respect FIFO property. So here's another little exercise. This is for looking at the network order, so the send and receive. So P1 broadcasts M1, and then goes to P2, and when P2 receives this, it broadcasts M2. But these broadcasts, of course, also go to the other nodes. So which one of these is respecting network order, and which one is not? What do you think?
The one on the left,
The one on the left is
respect.
respecting the order, because M1 is causally before M2. So here, M1 is delivered before M2, and M1 before M2. So that's good. But here, again, the order is switched. Huh? So the network order is not respected. So you see, we're looking at the nodes that initiate the broadcast and the nodes that deliver. Huh? Okay. So here's the final one, a little bit more complicated. So this is the transitivity. So here we have 3 messages. So M1 broadcast goes to P2. When it receives this, P2 then makes a broadcast, goes to M3, and then P3 makes a broadcast. And these messages then go to all the nodes. So all of the nodes have to deliver in the causal order. They have to respect the order between M1, M2, and M3. Okay? So which one, where is the respected and where is it not respected? Yeah?
The right,
The
the
right
right
one
one is
is-
respecting.
The right one is doing what?
Is respecting the rule.
Is respecting the order. Yeah? So, because we have M1 is causally before M2, before M3. Here we have M1, M2, M3, M1, M2, M3, M1, M2, M3. So they're all delivered in the causal order. Whereas here, for some weird reason, M1 is late here. It should be delivered before M2, but it's not. Okay, yeah, so that's right. So the left one is not causal, is not respecting the causality. Okay, so you can see how it works, huh? And you can see it's not the same as the causality that we defined with Lamport. It's not exactly the same, although it's very similar. Huh? Here we're looking at broadcast, and the only events that we're interested in is the initiation of the broadcast and the delivery of the broadcast. Huh? So all deliveries have to respect the causal order of the initiations. Okay? Okay. Let's now do a little bit of specification engineering. Okay? So this is important. You have to be able to think about specifications and compare them and do them. Before you write code, you have to engineer the specification. Okay? So here I'm now defining 2 variations of the causality property. So the first one is what we saw. PI delivers M1. PI must deliver every message causally preceding M1 before M1. Okay, fine. But there's a second one now, a variation. If PJ delivers M1 and M2, and M1 is causally before M2, then PJ must deliver M1 before M2. So in this second property, we're saying if the node delivers 2 messages, and there's a causal connection between those 2, then they have to be delivered in causal order. So these 2 properties are not the same. So it's important to understand the difference between the 2. So one way to understand the difference is to look at some scenarios. So it's possible to satisfy one of them and not the other. But not arbitrarily. One of them is actually strictly stronger than the other. That means if one of them is satisfied, it guarantees the other one is satisfied, but not inversely. Okay? So here's 2 scenarios. In the scenario here on the left, so CB says if you deliver M1, or then I have to deliver every message causally preceding M1 before M1. So P1 delivers M2. So the M1 here is M2, but M1 is causally before, but it's not delivered before. So this is violating CB, okay? But it's also violating CB prime, because P1 delivers both M1 and M2, and M1 is before M2, but they're not delivered in that order. Okay, so it's violating both of them. So that's interesting, huh? So here they're kind of the same, huh? CB and CB prime. The error here, the causal error, is violating both of them. But if you look on the right side, here we're violating CB, but not CB prime. Okay? So for example, why is that? Well, look at this message here. M2, it goes to P3. So P3 delivers M2. So according to CB, it must deliver every message causally preceding that one, which is M1. But it's not delivering M1. The M1 message is failing, has disappeared. Okay? So it's violating CB. But it's not violating CB prime. It's fine. According to CB prime, this is fine. That's kind of not nice. So CB prime seems to have a problem. So here, for example, P3, if a node delivers 2 messages, but here it's not delivering P1, so according to CB prime, if it doesn't deliver P1, then I don't care about the causality. Okay? So that's a weaker property, huh? CB prime is weaker. So you don't really, so CB prime is not really so nice, okay? So CB is stronger than CB prime, okay? So, but CB prime seems to be kind of too weak. So you have to be really careful when you make specifications. Because, I mean, at first glance, they don't seem very different. But in fact, CB prime is too weak. We don't want it. And one way to see that is to look at the form of the property. It's if-then. They're both if-then. But what's inside the if here? CB prime has a lot of stuff in the if part. If Pj delivers M1 and 2, that's a very big condition in the if part. That means CB prime is assuming a lot, huh? Whereas CB only assumes one delivery. Okay, Pi delivers M1, whereas CB prime assumes you're delivering both before it says anything. Okay, before it assumes anything. So CB prime is actually too weak. So we're going to reject CB prime. Okay. So usually, so when you make specifications, you have to be very careful because small changes can actually be very important, okay? So CB prime is too weak because it assumes a lot here, whereas CB is much stronger, okay? CB, if you deliver one message, you have to, all the ones causally before have to come. That's very nice and strong property, okay? Okay, so this is an example of what I call specification engineering, where you think about the specifications, okay? So whenever you see specifications, you should try to make small variations. And it's not usually easy, huh? You have to do some subtle reasoning. And one of the important things is the structure of the property. Very often they're if-then, okay? It's very important what's in the if condition, okay? So you should look at that, you should focus on that, okay? Okay, so now let's start making some algorithms. Remember, CB by itself is only safety property. So basically, it's outlawing certain kinds of executions. It's outlawing the non-causal ones, okay? It is saying it has to be this kind of execution. Any other one is outlawed. So it's like a rule a law that you have to follow, okay, when you respect it. So we're going to add this property to the regular reliable broadcast conditions. Remember, these are the 4 conditions you saw last time on reliable broadcast. So this is just the all or none property, basically. No duplication and correct node, etc. So all the correct nodes get it or none get it. Okay, but this one doesn't say anything what happens between 2 separate broadcasts. Okay, whereas CB adds a condition for that, and it outlaws some executions. Okay, so basically that's what it does. That's what the safety property does. Okay, and it's the same for uniform. We add the same CB property to uniform. So you see how easy and modular it is, huh? We only have to add the same condition to either the uniform or the regular reliable broadcast. Those are 2 very different algorithms. URB and RB are very different. URB is much more complicated. But we just add CB to both. Okay? So basically we're building our layered system. We're taking advantage of the event model and the layers. We're going to reuse all the code we did for reliable broadcast and build Causal on top. We're going to have, so we have this module already that's doing reliable. So basically there's best effort underneath, then there's reliable. Reliable is using best effort, remember? And then on top we will build another module doing Causal, adding just causality. And the module is like a filter. It outlaws some executions. It makes sure that things happen in a certain order. So it's keeping all the stuff reliable, but it's adding a little bit more strict management of the order. And we do the same for uniform. So we have best effort, uniform reliable, and we add also a module for doing causality on top. Okay? So this will give us reliable causal and uniform causal. And the only extra code we have to write is respecting causality. All the reliable stuff is already done. Okay? This is very nice, very modular. So the reliable broadcast is already implemented, debugged, everything. It's running. So if you want to make it causal, you just add a small layer on top. So this is a really good way of building distributed systems. And it took people a long time to figure this out. I don't know. Maybe this seems obvious to you. I don't know. But in the olden days, like in the 90s, this was not obvious at all, okay? That you could do this. But causality and reliability are actually very different things. Causality is an all or none property. Reliability is all or none, and causality is just ordering between separate broadcasts. Those are they're basically orthogonal, okay? Okay, so let's make an implementation. So we're going to make the simplest possible algorithm first. The simplest possible. So how do we do that? And we're going to follow the CB structure. So remember CB, if you deliver a message, you have to deliver every message causally preceding. What's the simplest way to guarantee that? Well, here's a very simple way. Every message, you piggyback history on top of it. And what is that history? It's all causally preceding messages. So at the node, each node keeps track of all the previous messages. And when you do a new broadcast, it just piggybacks all the causally preceding ones and sends that. That is really the simplest of, and clearly this is going to be correct, Okay, you will immediately say, yeah, but it's super inefficient. But that's bad thinking. You should not, that's a good reaction, but not now. The first thing you have to get is correctness. After that, we'll optimize. But so this is clearly correct, You see that, You also see that it's going to be kind of inefficient because the history will always be growing, But we don't care about that. It's very important not to care about that in the beginning, okay? So this is called fail silent, no waiting causal broadcast. So fail silent, because it does not need a failure detector. That's really nice, okay? We just use the reliable broadcast, and maybe it has a detector, we don't care. But the causality is just guaranteeing order, and it doesn't need a failure detector for that. So every message will carry an ordered list of all the messages in a well, I'll call the variable past M, okay? All the causally preceding messages to M. And whenever you RB deliver, notice now I'm looking at the layered structure. I have my causal block. The messages coming from underneath are the RB delivers, and the ones going out on the top are the CO. So maybe you can see what I'm going to do here. So here I have an RB deliver, and then above it you have a CO deliver. So this is my causal broadcast node, and underneath I have a reliable broadcast. So here I will be piggybacking, and here I will come back with this piggyback, and here on the top I will be doing just the causal broadcast and deliver. Okay? So when a node RB delivers, then it comes with this variable, past M, attached to it. M and past M. This module will then check. It will say, have I already delivered all the messages in past M? If I haven't, I deliver them. But it also avoids duplicates. It has its own delivered set here. But it checks to see whether it has delivered all the messages in past M. And if it has not, it delivers them. And after that, it delivers M. And that's it. So this is obviously correct, huh? What do you think? It's a very simple way of adding causality, huh? Of course, it's not efficient, but that doesn't matter. Okay, so here's some examples of executions. So this example is what I call direct override. You'll see why. So we have 3 nodes. So I'm now doing a causal broadcast. Okay, this will send to P2 and P3. Notice this one is very slow. It's very slow. It's only arriving near the end. Okay. And it will do a causal order delivery. Here, these are little red boxes, and a causal order delivery here. Very quickly, but the third one is somehow stuck in the network. It's very slow. Okay. Okay, good. Now I do another causal broadcast here on the same node, M2. Now, you notice there's this list added here, M1. This is the past M list. So M1 is all the causal messages behind M2. So there's only one right now. It's M1. So this one will arrive here and here. Okay, very good. Fine. Okay. It arrives here. The algorithm sees, it looks, says, I've already delivered M1, so I don't deliver it again, and I deliver M2. Okay? And here it's very easy, since I'm on the same node. But now look, the M2, M1 message is arriving at P3. So what's going to happen now? What do you think? What's going to happen? Because M1 has not been delivered. M1 is very slow here. Huh? So what's happening? So let me make it very, very clear. So I make the little green boxes are the RB delivery. So basically this little green box means that this message has arrived at the node and it's here. But it's not yet been CO delivered. Huh? Because it's now gone into the CO, the causal box. Okay? Now the causal box will look at this message, and it sees, I have not yet delivered M1, and M1 is causally before M2, so I have to deliver M1. So it does a CO deliver M1, and then a CO deliver M2. So basically, it actually does the delivery itself, okay, of M1. It doesn't wait for this one. You see that? And then what happens later is when the M1 arrives here, it sees that M1 has already been delivered, so it does nothing. Okay? So you see how it works? pretty straightforward, huh? So this is called direct override because this M2 is kind of overriding the M1, okay? It's direct because they're both coming from the same node, but it could also be indirect, as we'll see. Yeah?
Are all the informations contained in the past list from M2? Of M1?
All the past messages are in there.
In the messages, informations.
It's a list of past messages. That's all you need. In the order of, in order, okay?
Doesn't P3 needs the informations from M1, the content of the message?
But it is, M1 is the content. M1 is the full message, the full data structure. Of course, it's big, huh? So maybe M1 is a big data structure. Well, it's in there. Everything, it's the whole message. It's not just the name of the message. It's the whole actual message. Maybe it's 10 megabytes. It's a big chunk, okay? Yeah. So you will say, you're saying it's not efficient, right? But you have to, you have to resist the tendency to optimize. We know that it's correct. We will optimize it, don't worry, later. But you see, you'll see that optimization makes it more complicated, and at least this is correct, huh? See that? Yeah, so you resist this algorithm, huh? Because it's not efficient. Okay, here's another execution. So similar. Here it's what I call an indirect override. You'll see why. So again, P1 does a seal broadcast, M1, which goes to P2, P3. And again, M1 is very slow here. Okay, very good. Things go on. M1 is delivered both on P1 and P2. This is good, huh? And then it's P2. P2 that now delivers, that broadcasts another one. So P2, not P1, huh? The previous one was P1. But P2 broadcasts M2, but it knows that P1 is before. So it's the same list M1 here, because M1 has already been delivered here. So the P2, even though it's not the same node that has broadcast M1, it knows that M1 is before M2, because it's been delivered before on the same node, okay? So this has a local past M list, which is piggyback on the message M2, okay? Yeah?
So each message contains the expeditor ID, or I don't know, because the network
Each
packet.
message is unique.
No, I want to say on network packet you have a source IP, but if P2 sends
Yeah.
M1, so the acknowledgement go to
Yeah.
P2.
In this case, we don't need to know that M1 is originally coming from P1.
Okay.
All we need to know is that each message is unique. Okay? And that means it is, if I send a message, then there will never again be a message like this one. Every message is unique. Okay? So that means M1 has already been delivered. This M1 is the same as this one, huh? On P2. And then I do a broadcast. So I know for sure that M1 is causally before M2, and this is a unique identity. Okay? So it's not just a record data structure. I mean, with some information, it also has a name. Okay, it's unique. Okay, all messages are unique. This is an important rule, huh, that we have. This makes it easy to implement this, huh? So the M2s here will be delivered on P1 and P2, but what happens again at P3? P3 again is the joker. So we're going to have an RB deliver, the green box. So you have to clearly understand the difference between the green and the red boxes, huh? Both of these are messages coming to P3, but the RB is coming into the RB box, which is underneath here at the bottom, whereas the CO delivery is coming out of the causal box, okay? So the causal box will receive this RBD and then do its thing, huh? So it sees that M1 has not yet been delivered, So it delivers M1 and M2, and the same thing happens as before, basically. So this is an indirect override because this M2 message has overridden the M1. The M1, we don't even care even now that this one arrives, okay? Does nothing. We've already delivered COD M1, okay? So that's very nice, right? So this algorithm is clearly correct, huh? Question?
What is the difference between the causal box and the RB delivery box?
Between this, the green and the red one?
Yes, yes, I know.
So it's because we have a layered system. Because we want to understand what this is doing. So we have a causal broadcast and reliable broadcast. We do COB, and this causes a reliable broadcast, and this one goes to best effort. And then we have a message coming back, which is RB deliver, and here we have a CO deliver. So RB deliver means that the causal box has received a message. Whereas CO deliver means that the application has gotten the message. Okay? When I do an RBD, the application sees nothing, huh? The application which is on top here. Huh? So it's important for us because we want to understand how this causal box is running. So it's important to know when the CB gets the message. So the green one is the message coming into the CB.
So the CB in the set of the computer can be seen as the kernel and which part of the computer?
So all of this is running on one node. Huh? This is all running on P3. And this is our layered, this is a piece of code. This is a piece of code, our layered code. Messages go down and come up. And they will go across the network, be underneath here. Huh? So the CB box is built on top of reliable broadcast. This is the code we saw last week. Huh? So CB is only talking to RB. It's sending RB broadcasts and it's receiving RB deliveries. Okay? So these are two separate pieces of code. Each of them is single-threaded. But both of these are basically running concurrently. Huh? But inside each box, it's a single-threaded thing. Huh? Is it clear? I tried to be very clear. Huh? It's very precise. Huh?
Thank you.
So the RBD comes here. So this is the green one. Then the algorithm that we're doing now, it does its thing. And it will send two messages up. See, one message is coming in here, but two messages will now go up here. So the number of messages going up and down is not the same. A message might come in here and nothing might come out. Or many things might come out. So when M1 arrives here, there's another green box here. It's the RBD M1 here. But this one, nothing will come out on the top here. So I don't write it, but there's another green box here. See that? That's very precise. If there's anything unclear, ask the question, because it's very precise what's happening here. Okay. So that's the algorithm. I have to show you the code now to this algorithm. Okay. So the code is not very complicated. Well, it's basically two pages in very large font. So this is reliable causal order broadcast, which I call RCO. It uses reliable broadcast. So there's the two boxes. I have a delivered structure. I also have this passed Vista. So when I get an RCO broadcast, so this is the event coming in, I will trigger an RB broadcast, and I will add M to the passed list. Okay? So that's basically, I also add, I'm not sure that the name, I mean, it's also saying where the message is originally coming from. I'm not sure that's actually needed, but we'll see. Okay. So it appends it to past history. And why is it not going to the next one? Okay, so this is the second side. So this is basically the body of the code. There's one event with lots of code here, but it's actually not very complicated code. So the RB deliver, this is the message, the green box, coming from the bottom. First of all, it checks whether M has already been delivered or not. no duplicates. If it has not yet been delivered, it will look at all the messages in past list, and if each of the, so they're done in order of causality. Okay, if the message has not yet been delivered, so N is a message, then it does an RCO deliver. So maybe there's many RCO delivers coming up here. It adds N to deliver, and of course it adds N to the local past list. Whenever a CO delivers a message, it updates its own little past list. So it does this loop here, and then it does its own RCO deliver. It makes sure there's no duplicate, and it adds M to P. And the reason why that the originating node is part of this is because when I do a CO deliver, it actually tells me where the originator is. Who is the originator? So I have to keep track of the originator. Right? That's why it's a pair. It's not just the message, but also the node that originated it, because that's what has to COD. So I go in ascending order, I deliver the preceding messages, if they've not yet been delivered. I append to the local history, past is a local variable. And then when that loop is done, I deliver the current message, and I also append it to this tree. And that's it. Okay? So this code seems very complicated, but it's actually quite straightforward. You see that? It's actually not, the logic is not complicated. You see that? You should understand very clearly the logic. Okay, so let's make a small break here. And then we'll try to make things efficient. See, there were some people annoyed that this is a very slow algorithm. And it is slow. So after the break, we'll try to make it more efficient. So we'll make a small break. So the idea is we have a CB box built on top of an RB box. And the RB box satisfies 4 properties, RB1 to RB4. And the question is, does the output of the CB also satisfy those? And that is something you can check fairly straightforwardly, okay? So there's 4 properties, RB1 through RB4. So no creation, no duplication. That's pretty easy to see when you look at the code. The CB code is not creating messages. It's not duplicating messages. It's basically just changing the order in which messages are delivered, okay? Validity, okay? So the all or none property, okay? So with the validity and the agreement. So basically together it's the all or none property. It's the only thing that the CB box is changing is the order of delivery. Some messages might be delivered earlier because they're in the past list, never later. So validity is still satisfied, and agreement is also satisfied. You just have to look at the RB and look at the code. So that's very straightforward. Those are the RB properties. Now the causal property, this is the new one. So we basically just added 1 property to those 4, CB. So this causality is a thing that is a sequence. So you have a sequence of broadcast events. It's growing starting from when the algorithm starts. So it has to be done on induction. Starts with empty sequence, and each time you broadcast, it gets a little bit bigger. Okay? So you have to assume it's true for all deliveries of a prefix of the execution, and then you extend it by 1 event. Well, you can see that you're delivering the causally preceding ones before. So you can show that it will stay true when you extend by 1 event. So it's pretty obvious, actually. Okay? Okay, so that's correctness. Now there's an efficiency issue here. Okay, so the disadvantage of the algorithm, which people have noticed, is that the message size grows with the execution. So there's different ways of improving that. In fact, there's many ways. I'm going to show 2 ways. One idea is to garbage collect the old messages. Basically, that past list is growing bigger and bigger, But eventually, you don't need a lot of that. A lot of those messages are not useful anymore, okay? So, when all correct nodes have gotten and delivered the message M, there's no need to keep it in the passed list anymore, okay? So basically, you have to detect that. When have all correct nodes got the message M? Because notice there can be failures still, huh? So you will acknowledge the receipt of the messages. When all correct nodes have gotten it, when you know that, then you can delete M from the past. Okay, so that's a garbage collection algorithm. Notice because you have failures here, you have to know when correct nodes got M. That means you will need a perfect failure detector. And that is, unfortunately, a general problem. Distributed garbage collection is extremely difficult. That's another way of saying that it needs a perfect failure detector, okay? So with a perfect failure detector, you can implement garbage collection. So the idea is clear, huh? When all correct nodes get the message, I can remove it from the past list. So I can show you the code for this. So this code is basically added to the previous code. I don't have to change the previous code. This code is modular. So I add extra code in the CB box, which basically will remove elements from the past list when they're not needed anymore. Okay? And you need extra data structures. So the extra data structure is you need to know which are the correct nodes, and you have to know whether messages have been received by all correct nodes. You need an acknowledgement vector. So when you have a perfect failure detector, so when you get a crash event, you remove PI from the correct set of correct nodes. Okay? Now, when you deliver an event, then you add it to the local acknowledged list, and you do an RB broadcast. So basically, when I do a CO deliver, I tell everybody, I don't need, M has been delivered by me, it's okay. Okay, so you do an RB broadcast. Okay, so that's an RB broadcast. So I'm using reliable broadcast to send acknowledgements. Okay, and then I deliver, when the acknowledgement's delivered, I add it so that every node will now receive this. And for each node, if all correct nodes have acknowledged M, so that's the way I read this, huh? Then I remove M from the past list. So I'm garbage collecting the past list. So the price is you have some extra messages on the network, but the past list will always be shrinking in this, okay? So there's some comments here. So the bookkeeping. So this is called upon CO deliver. So when I CO deliver, I broadcast the acknowledgement to everybody. And when I receive an acknowledgement from all correct nodes, I remove it from the past. So this is a pure garbage collection algorithm. Huh? Okay, a few questions on this code. So this is the whole code. Huh? Few questions. 2 questions. Well, have we ever actually solved anything? The ACK-M array is also growing with time. How do we garbage collect it? So this actually is easy to solve, but I add this question because it's important and it shows whether you've actually understood. So how do we garbage collect the ACK-M array? What do you think? Because otherwise we garbage collect past, but this ACK-M array also keeps growing, huh? So well, that has to be garbage collected too. So what do we do? What do you think? It's actually not hard, yeah?
We don't need to keep the ACK-M if we remove M from the pass list. So
exactly.
we can just
We can actually add a statement here, also removing from ACK-M. Huh? So if when we remove M from past, we won't need ACK-M anymore either, in the future, once it's been removed. So this will also cause ACK-M to shrink. Yeah? So I didn't put the code here because I want you to think about it, but that's exactly the right answer. Now, another question, a more nasty one. So the garbage collector actually uses a perfect failure detector, and it will remove an element if all the correct nodes have acknowledged it. Now, a perfect failure detector is kind of hard to do on the internet. What happens if we use an eventually perfect failure detector? And first question, does the garbage collector still work? Why or why not? Would it still work or not? What do you think? So you notice, remember what this does, huh? Eventually perfect failure detector is allowed to make mistakes. That means it's allowed to incorrectly assume that a node is crashed when it is not actually crashed, but only temporarily. After a certain time, it will make no more mistakes. Huh? So if we have that, does the garbage collector still work? No, why not?
Because if he assumes you crash and you don't, so it can assume you don't have to hack it and
Exactly.
remove
So if
it
you
from the
assume, so if the eventually P, it can make a lot of mistakes and it can assume everybody has crashed, so you can prematurely remove elements from the past list. So you assume that a bunch of nodes have crashed and you remove M, but then you notice, well, actually they have not crashed yet and we still need M, okay? So the garbage collector will not work for an eventually perfect failure detector. That is not a fault of this particular code. In fact, garbage collection, distributed garbage collection is very hard and is basically theoretically impossible. And you see that in practice. So for example, something which is not on the slides, if you write a distributed program in Java, for example, where you do remote method invocations, so you can have references to remote objects, okay? And you can have many references to some object for many, many nodes in a Java program. But Java, of course, has garbage collection. So how is that node garbage collected? Well, Java uses a trick called lease-based recovery. So it basically uses reference counting garbage collection, but I won't get into only sometimes is able to recover. But it basically uses something called lease-based. That means everybody who needs that object has to tell the object, I still need you. So you basically lease it. You hire like the object for a certain time. I will need you for at least 1 more hour. So I send one message, and the object knows it has to stay alive at least 1 more hour. But what if that message doesn't get through? Well, then the object will be incorrectly garbage collected. That means a Java program will sometimes incorrectly collect things, okay? And that's kind of inherent. Garbage collection is actually very hard to do, and I think it's theoretically impossible in a partially synchronous system to do a 100% correct distributed garbage collection. But you can do 99%, okay? Okay, so that's garbage collection. But I can do another implementation. Okay. Now, our first algorithm was the most naive one you can imagine. Every message carries a full history of all the past messages. And you ensured causality before delivery. That was our first algorithm. We can already imagine how you can do things in an easier way. Maybe you don't want all the messages, okay, the preceding messages. Maybe you just want some information about those messages, okay? And the idea is to use vector clocks, a vector timestamp. Basically, each node will remember how many messages it still has to get from each other node. That's just a number. It's much more efficient than a list, okay? So if it sees there's missing messages, it just has to wait until they arrive, okay? So that gives us a second algorithm, which is much more efficient than the first algorithm. This is called the fail-silent waiting causal broadcast. Again, this algorithm has the advantage, it needs no failure detector, and it represents the history by a vector clock. So I'm attaching a vector to every message, and the nice thing about that is it's constant size. It's not growing with the history, okay? And of course, if you have a lot of nodes, it's still going to be less efficient, but at least it's going to be much more efficient than the full history-based algorithm. Okay, so what information is in this vector clock? So remember the vector clock we saw that when we talked about causality? So each node has a vector, and that vector basically tells me how many causally preceding events there are on all the other nodes. Okay? So that's why you need a vector of n. Huh? We're going to do similar thing, but we're only interested in broadcast events now. We're not interested in the whole execution, okay? And we're interested in two kinds of broadcast events, CO broadcast and CO deliver events, because they determine the whole thing about broadcast, okay? So at node PI, we will have a vector, VC, with n elements. The index I is the number of messages that PI has itself broadcasted, okay? And the other elements is the number of messages that it has delivered that come from other nodes. So basically the number of causally preceding broadcasts on each other node. And it knows that because it will receive them and it can keep this vector up to date. Huh? It's like the vector clock. So it's a vector clock, but not for all events, only for the events that we're interested in, relevant events, which is broadcast. Okay? So of course this is much more efficient, but in some sense the algorithm will have to do some weighting, and we'll see how it works. Okay? So basically it works like this. When I do a CO broadcast, I will piggyback the vector clock to the RB broadcast. So when I do a CO broadcast, I will attach my vector clock and do an RB broadcast. And when I have an RB delivery coming up, the vector clock will be attached to that. I will compare the piggybacked vector clock with my local vector clock. And I will see whether there's a gap. And for example, if this one is much more recent, if the numbers in VCM are much higher, that means there are messages that have not yet arrived at PI, but that should have arrived, that are causally before. So I will have to wait. So the local VCI will keep increasing when messages come, but the VCM, the piggybacked one, maybe it says there are 3 messages coming from P1 that are causally before me, and maybe VCI says, well, I haven't seen them yet, so there's a gap. So the VCI will be growing, okay, as messages arrive, so it has to wait until VCM is less than or equal to VCI. Because VCI is growing, and eventually the gap will close, and then it can deliver. So basically it has to wait, okay? But let me show you an example of how it executes. So here I have 3 nodes. So the vector clocks are 0, 0, 0, beginning, okay? P1 will do a broadcast. When it does the broadcast, its vector clock becomes 1, 0, 0, but it sends 0, 0, 0 as piggyback. This means the number of causally preceding broadcasts that have been done. So these are both zeros, huh? Okay, good. Okay, it can deliver locally, clearly. And what about this one? P2. Well, 0, 0, 0 is the same as 0, 0, 0. There's no gap. So it can deliver locally. There's no missing messages here. And it increases the local vector clock to 1, 0, 0. That means it has 1 broadcast from P1. Okay, that's reasonable, huh? Okay, now P1 does another broadcast. So the vector clock then becomes 2, 0, 0. I've done 2 broadcasts. And on the message M2, I piggyback 1, 0, 0. So 1 is the number of broadcasts before, 1, 0, 0 here, and 1, 0, 0 here. Now notice, as usual, M1 is a very slow guy, so it has not yet arrived. M2 arrives first, but it's 1, 0, 0. But the local vector clock is 0, 0, 0. So there's a gap. What that means is that M2 knows that there's one message causally proceeding from P1, but P3 has not yet got that message. That means I'm not allowed to deliver M2 yet. You see that? It has to wait. Okay? Yeah, the others will deliver here. So I keep this one. Basically, it's stuck, it gets stuck in the RB module. It's not, sorry, it gets stuck in the CB module. It's not brought up to the application yet. I hold it. And eventually, a little bit later, the M1, the slow one, will arrive. And this one has 0, 0, 0. So there's no causally preceding messages. And that number is also the same. That means I'm allowed to deliver. And then the local vector clock becomes 1, 0, 0. I now have received one causally preceding broadcast from P1. Okay? And now I can deliver M2. Because M2 knows there has to be one causally proceeding from P1, and I got it. You see how it works? It's not that complicated, huh? And so I can deliver it. And then the local vector clock at P3 will also be 2, 0, 0. You see that? You see how it works, the algorithm? So you just basically, if you have good intuition on the vector clocks, it's not that complicated. Huh? What the vector clock means. Okay. Okay, let's look at some code here. So this one is the next one. So the fail silent waiting. Again, it uses reliable broadcast. It has its local vector clock, which starts out being zeros. Now, when there's an RCL broadcast, it will do an RB broadcast. It will increment its local vector clock, because clearly I have just done a local causal broadcast, and it will do an RCO deliver. So everything on the same node. Okay? Notice, yeah, VC is piggybacked. This is the number of causally preceding broadcasts. So I piggyback it before incrementing, because I don't want, it doesn't count itself, huh? It's the preceding ones. Okay? And I'm allowed to deliver. Okay? Clear. Now things get more interesting. Because when there's an RB deliver, when the message comes up from RB to the C causal module, I'm not allowed to deliver right away. Okay? Okay? I'm not allowed to deliver right away. I add it to a set called the pending set. So I basically hold it. Okay? And it has its piggybacked vector clock. Okay? So whenever an RB message arrives, I add it to the pending set. And then I have to check, because messages can be arriving all the time. And I run this separate piece of code, which is a procedure called deliver pending, which is essentially a loop. It notices whether any of the held messages can be actually delivered. So this is exactly what we saw in the scenario. So it's going to, let me put on hold. So for every message whose VCM precedes the local VC, what that means is that there's no gap. That it had come at least to that level. It can get higher because there might be non-causally related messages that are incrementing VC that have nothing to do with it. But it cannot be less. Okay? It has to be less than or equal. If it finds one, it removes it from the pending set, it RCO delivers it, it updates its VC, and it keeps looping, because maybe there's a whole set of them that have to be delivered. Huh? Maybe if I If I close one gap, then another one can now become delivered, and so on. But there might be a sequence of them. So it's basically a while loop. Okay? It's doing what I showed you in the scenario, but in general. Okay? Okay, so here's an example to get you thinking a little bit. Assume I now have two nodes, P1 and P2. So the vector clocks are 0, 0. P1 does a broadcast. So the vector clock becomes 1, 0, and 0, 0 is piggybacked. Now P2 does a broadcast. Okay? So the vector clock of P2 is increased to 0, 1. The piggyback is 0, 0. Okay? Now what happens here? What happens? Well, 0, 0, 1, 0 is not less than 0, 0. It's actually strictly bigger. That's kind of weird, huh? It's strictly bigger. I mean, in the previous case, example, when the gap was empty, it was basically the same. But here it's actually 1, 0 and 0, 0. So that means we're actually allowed to deliver here, and the vector clock becomes 1, 1. Okay, and in the other direction, we have a similar behavior. We're allowed to deliver, and the vector clock is also 1, 1. Well, this is interesting. So here we have D1, M1 is delivered before M2. Here we have M2 is delivered before M1. So the delivery order is not the same here. So what's going on here? What's wrong here? Is there anything wrong here? If there is, what's wrong? What's happening here? Is that reasonable? What has happened? You have to understand causality, yeah? To understand what's going on here. Events are not necessarily, all events are not necessarily causally related, huh? So what do you think? Is this fine? Is it good? Or is there a problem, or what? Okay, let me just go back a little bit here. So when this one comes here, in the previous, assume that there would have been no broadcast here. The number would have been 0, 0. Okay? And that means that there are no causally preceding events here, here. And so it's okay. But now I do an event, and this one becomes 1, 0. It actually becomes bigger. It's kind of like, it's weird. It's like a negative gap. What's going on here? But it's actually logical. Because what's the causal connection between BM1 and BM2? What's the causal connection between these two events? Come on. What is the causal relationship between BM1 and BM2? Is there a causal relation? What do we call events like this? Pairs like this? Concurrent events, huh? There is no causal relationship between BM2 and BM1. So we totally do not care about the delivery. There's no condition whatsoever on the delivery order between BM1 and BM2. The causal module will enforce the order for causally connected messages, not for concurrent messages. So there's nothing wrong here. This is a perfectly normal behavior for this algorithm, okay? And it shows you also why the vector clock can actually get higher. So it's like, it's not even there's a gap, there's more things. But those extra things are not causally connected to the, so here I have 0 causally preceding messages. Here I have 1 causal message. Well, this one asks for 0 messages preceding, and here I have 1. So clearly this 1 is not causally connected to M2. M2 doesn't care about it. Okay? See that? It's interesting, huh? So this algorithm is much more efficient. It's still not totally scalable. If you want to optimize more, then please, there are many papers and research on optimizing more. I actually had a PhD student, Manuel Bravo, made a system called Saturn, which very efficiently is able to determine causality for very large and dynamic systems, but it's not 100% correct. Okay? But it's good enough that it gave him a very nice PhD. Okay? So causality is actually hard, huh? Okay. Okay, so now let's do some precise thinking on ordering some broadcast. So we have seen different orders. We have seen causal order. We have seen total order, where all the messages are arriving in the same order on all nodes for the broadcast. We also have single source FIFO order, where 2 messages sent from the same node will arrive in the same order, but there's no other condition, so there's no transitivity. So these are orders. So the single source FIFO order is defined like this. So intuition is messages from the same node are delivered in the order they were sent. Okay, and here's the formal condition. Okay, if PI broadcasts M1 before M2, and if PJ delivers M1 and M2, then PJ will deliver M1 before M2. FIFO between PI and PJ. Okay? Okay, so that's a condition. Notice I don't care whether the messages are delivered. This is only for delivered messages. Okay? Notice inside the if, the delivery is part of the if condition, huh? So I'm only worried about actual delivered messages, okay? Okay, that's an order, right? That's clear, right? Single source FIFO. Total order, this is something we actually saw in the very first course. Everyone delivers in exactly the same order, okay? For all messages and nodes, if PI and PJ deliver the messages, then they deliver them in the same order. So for every pair of messages, the order is the same. Okay? So again, this total order condition doesn't require delivery. Huh? It's only true if the messages are delivered. Okay? So it's not going to force the delivery. Another point is, it's the same order, but it's not necessarily the order in which they were sent. Okay? That's not part of total order. It's only the same. Okay, so now we have 3 orders. Single source FIFO, totally ordered, and causally ordered. And now here's some exercises to think. Okay, I have 2 nodes, broadcast A here and B here. Here I deliver A and then B. On the second node I deliver B, then A. Now, my question is, does this execution satisfy single source FIFO? Does it satisfy total order? Or does it satisfy causal order? You have to be very, very careful here because of the if conditions, huh? So does this execution satisfy single source FIFO? Okay, just very briefly, single source FIFO. If PJ delivers M1 and M2, they were sent from PI, then they were sent in M1 before M2, then they would be delivered M1 before M2. So is this a single source FIFO execution? What do you think? What do you think? I see someone nodding their head yes. Yeah? That's actually a correct answer. It is a single source FIFO, but it's vacuous because there's no two messages sent from the same node, so it's vacuously true. What about total order? Okay, so it's a single source FIFO. What about total order? Is this execution satisfying total order? Someone else. Is it that's pretty easy to check, huh? Come on. Is it satisfying total order? Yeah.
No,
No. Why not?
because for the first one it's A then B, and for
And
the
here
other
it's
one
B then A. Absolutely correct. It's not total order. What about causal order? Here also it's a little bit subtle. Is this execution satisfying causal order as we defined it? The first question you have to ask is, what is the causal connection between A and B? What is the causal connection between A and B? Someone else. These two guys have already answered. Someone else, someone from the back. What is the causal connection between A and B? Come on. Is any one of them depending on the other one? No, so what is it? Concurrent, yes. So A and B are concurrent. So what does that mean in terms of the delivery order? That means the causally ordered, causal order doesn't care, okay? So that means even if they're different, doesn't matter. It is causally ordered because the concurrent events, there's only concurrent events, and for concurrent events, we don't care. So the causal order condition is happy, is satisfied, okay? So here's another example. You see the kind of subtleties going on here, huh? Now A and B are both broadcast from the same node. A and then B. So is this one a single source FIFO? What do you think? Single source FIFO, broadcast from the same node. Delivery. Huh? Come on, there's no risk.
It's not,
It's not, exactly. It's not. Why not?
because the second node delivers B before A.
Absolutely. It's not a single source FIFO. I mean, it could have been if these would have been switched. So it's not a single source FIFO. What about total order? Is this a total order? Is this satisfying total order? What do you think? Someone else. Most people answering have been kind of close to the front or the edge. What about this middle group here? No, there's one guy who didn't answer some. There's a couple of guys who didn't. Is this satisfying total order? What is total order? Come on. It's not that complicated. No? Well, I mean, BA, BA. Doesn't seem to be very complicated, right? It's total order. What about causal order now? I thought I heard something. They're not causal. And the reason is, here, the order is switched, huh? Because A is causally before B. That's the case. So it must be delivered before B to satisfy causal order. So it's not causal. Okay? A final one, just for some more fun. Now A and B are causally connected, but they're on different nodes. So I broadcast A here, and then after this one is delivered, I broadcast B. So is this a single source FIFO? What is a single source FIFO? Single source FIFO. Ting, ting. Is there a ting, ting in there? What do you think? There is no ting, ting. So what does that mean? That what?
It is.
It is single source FIFO. Yes, vacuously it is, because no one is making it false. Okay? What about total order? This is pretty easy, yeah?
It's not.
It's not, clearly, because, well, A is before B, and we have B delivered before A up here. Huh? What about causal order? Should be easy, yeah? Right?
It's not.
It's not causal order. Huh? Very good. So you guys are slowly getting there. Huh? Okay, let me slowly show you. Let me show you this diagram. Notice here I'm basically summarizing all of the broadcast algorithms we saw. Well, we didn't actually see the code for all of them, but we saw the code for a lot of them. Best effort is easy. Reliable causal, uniform reliable causal. You could add causal to best effort. That's very easy. FIFO is very easy too. It's a simplification of causal. You're only worrying about the source. You don't care about transitivity. Okay, we saw uniform reliable. There's a lot of, so I guess you didn't imagine that broadcast was so weird and subtle, huh? Look how many different variations there are of causal. And we saw basically the code for all of them. Or you can derive the code. We saw enough code that if I ask you for the code for any one of these, you should be able to give it to me. Okay? So on the exam, I could ask you for reliable FIFO. But only the module, I can say, given a reliable broadcast module, please show me the code for a module that adds FIFO order to this. I could ask that. And you should be able to do it because it's simpler than causality. Or I could say, I'm given best effort, show me the code for adding causality. Even though we didn't see it, it's easy. Because if we're talking about this layered structure here, you can add causality to anything. It's just a restriction on possible executions. So you accept whatever the low level does, but you change the order a little bit so that it's causal, basically. Okay? Question for you. Okay, you notice there's 9 variations here, but we didn't see total order. Where does total order fit here? Where do you put it in this diagram? Where would I put it? Here, or here, or where? There? Where would I put it? Total order. Total order is actually very different than causal order, huh? Because as long as the order of the deliveries is the same, it doesn't matter if it's causal or not. It's funny, huh? As long as the order is the same, it doesn't matter if it's uniform or not uniform. If there's the order of the filled nodes, who cares? As long as the order of the deliveries are the same, we're good. So where does total order fit there? Yeah?
On the left part.
What do you mean? Where exactly?
On the first column.
In the first column.
Mm-hmm.
So what's the connection between total order and causal? Could I have a total order causal broadcast? But I could have a total order broadcast that's not causal. I could. I showed you an example. And I could also have a total order broadcast that is causal, right? You just have to enforce both the total order condition and the causality condition. So total order is like orthogonal to causality. Yeah? In fact, it's orthogonal to this whole thing. So it would be a third dimension here. If you add total order, you basically multiply by 2. Each one of these can be made total order or not. That means you have 18 variations. Oh, that's terrible. Maybe I don't ask you for the code for this, but for the ones you see here, I can ask it to you. You can see there's 18 variations. It's amazing, huh? How can something intuitively so simple as broadcast be actually such a nasty beast with so many variations? Welcome to the world of distributed systems. That's life. Of course, whenever you have an application, you will need one of them. Do I need causality? Maybe, maybe I don't. Do I need uniformity? Uniformity is talking about failed nodes. So if I don't care whether a failed node delivers or not, then I don't need uniformity. Okay? total order, that might be interesting for distributed database when I'm updating transactions, okay? If there's 2 copies of a distributed database, they should be the same. So the order has to be the same. So it all depends on the application, okay? Okay, so let me stop here.